proves. So now that we understand what Seaborn means to us, at least at a very introductory level, let's revisit the idea. How do we, when do we use that? Now, just because I'm trying to impress upon you, Seaborn is, very powerful and helps us a lot with single command, doesn't mean that you always do it. Doesn't mean that you always include it for no better reason than I think it's better to include it, right? Okay, so uh, what I want to share with you here is that when we want to have certain intention, communication intention or business intention, for example, suppose we want to show trend. We're trying to say, you know what, customer, you better buy this stock because it is growing. Now, you can keep saying it's growing and increasing in price, it's just very hard to convince people. But if we show a chart that is rising and rising, can you argue with that, right? I mean, we honestly will get the stock price and plot it, and it is showing an upward trend. So it's much more convincing if we want to show trend with a chart. If we are reporting to our boss and say, boss, the completion rate is really good, even though there is a lot of lockdown and stay at home and all the slowdown in activities, our progress is well. Now, again, you're reporting to boss, and this can sound suspicious, right? But if you show a progress chart using trend lines, using line charts, and it is kind of moving with constant gradient as time passes, then yeah, it is pretty convincing, right? It is a silence convince. You don't need to say a lot of words. In fact, the more you say, the more suspicious it sounds. Now, much as you can show progress, you can also show decay. For example, we might say that, well, recently the number of COVID-19 cases have come down. But come down, is it like creeping slowly down with a very strong resistance? The numbers are just not dropping, even though it's dropping one by one, but we are at a staggering 5,000. So dropping one by one doesn't mean anything. Or is it really showing meaningful drop? So it's like halving every day. Oh, that's great, right? Or is it showing kind of slow drop, like decreasing by 500 every day? What kind of drop, what kind of decay are we talking about? Something that is very heartwarmingly progressive, as in it is slowing down very drastically, or it is nervously uh, positive. That means it's encouraging, it's slowing down, but it's slowing down linearly. It takes a long, long time for it to go to zero. So what kind of pattern are we seeing? Do a line graph. We might want to show distribution, frequency, spread. Okay, is it ranging from high pitch to low pitch to low bass sound? So in terms of sound, we know what is frequency, right? High pitch and low bass sound. But there is also a sort of corresponding high pitch and low bass sound from the data, because when certain numbers occur a lot, they can form the lower side, the lower range or the upper range. What data occurs a lot, and that is the high pitch, the high frequency value. So the value itself, is it high pitch that occurs a lot, or low sound that occurs a lot? All these can be best shown using distribution, frequency spread, and if you want to show all these, use a histogram. Notice that in histogram, time, the essence of time is gone. The time element is destroyed. So the occurrences of high data, large data, can be towards the end or at the beginning, and the histogram shows the same, right? So because we are emphasizing the frequency, not when it occurs, right? So in those situations, we show histogram. To illustrate extensiveness of majority dominance, we can use pie chart, because look, a lot of us, a lot of this population desires having vaccinated, according to one survey. Now, what do you mean by a lot? 51% is a lot, or 30% is a lot. The rest are not sure, because 70% they are not sure. So 30% is a lot. So what exactly do you mean by majority? Then plot the chart, right? 70% said positively that they want vaccination as fast as possible. Okay, good. That illustrates everything. So pie chart will show dominance because whether 70% or 69% or 72.11%, it's sort of not so important, right? We should have the responsibility to calculate carefully, but it's not swinging the vote or the decision, as you probably understand what I'm saying. So it's already very much a majority, and anyone seeing a pie chart having that dominance should be convinced that, yeah, the majority says so. Doesn't mean you yourself must agree, but you should agree that the survey does say that, majority says so. Huh? Now, at times, we are not illustrating all these, not progress, not distribution, not majority. But we are trying to compare categorical quantity between measurements from different groups. All right, so it can be um, percentage of sort of percentage of population getting infected again between those who haven't got a shot of vaccination, having one shot of vaccination, and having two shots of vaccination completed the course. So, what sort of likelihood do these populations, do these people in different categories get? What sort of probability do they experience? So, using bar chart might be good to illustrate, multi-group comparison very quickly and very pleasingly, uh, sort of illustrating the difference or else the lack of the difference, because all the bars are kind of like going slightly up and down, which is not significant, or one bar is, clearly visually significantly double the height of the other, and then everyone is convinced, right, that this must be the category, whatever they are discussing. So here, to highlight categorical majority, we can also sort the bars and show the tallest bar on the left and the lowest bars on the right. And this usually is the kind of bar chart that we show. So we don't show the bar chart for non-comparable categories. For example, um, groups having 0 vaccination, 1 dose versus 2 dose. Now, if you go by number of doses, and because scientifically doses kind of reinforce the defense against viral infection, it can be considered a comparable category. Comparable means 2 will be better than 1, 1 will be better than 0. But for absolutely non-comparable categories, such as staying in block 1 versus staying in block 2 versus staying in block 3, so even though it's 1, 2, 3, the numbers mean nothing, right? It could have just been A, B, and C, alpha, beta, and gamma. So when they are totally not comparable in the categorical value, then typically the bar chart ends up being Pareto charts because we will sort by frequency. And then the discussion becomes, wow, this is really very frequently occurring, or this is most popular. So if we go by, for example, YouTube videos, right? Um, Out of these 10 videos that I made, which one is the most popular? So we can go by the number of likes, right? And then we sort of compare. And when we plot the likes with a bar chart, we might sort the highest like on the left and then decreasing towards the right. And so at one glance, we straight away look at the x-axis and say, oh, this video is the most liked, the one on Seaborn visualization. Okay, good. So yeah. Next and finally, to compare more detailed numerical distribution spread, and this is extremely popularly used across definitely finance industry and many other situations, box plots, right? Because box plots, they don't just show the lines are very meaningful. They show the spread. If the box is very elongated, it's widespread, high risk, high standard deviation. It shows the mean, and we can compare meaningfully across different boxes because the means are comparable. It shows extremities. Sometimes set of data might have high or large positive extremity, but very little to no negative or small or minimum value extremity. So all these are shown easily. One look we can tell. And then nice thing about box plots is it doesn't show one set of data. It's designed that we can quickly compare with 2, 3, 4, maybe even 10, but perhaps not more than that. So 10 sets of data, very conveniently compared. All right. So this is basically the idea of intention-driven plots. We don't say, let's plot something. What do we want? Okay, let's just plot a bar chart and see. You don't do that. You go the other way around. What do we want to tell our readers from this data set? Okay, and then you decide roughly according to this this list of bullet points. Okay. Now, question time. All right, so a little bit of an exercise. Suppose now I present to you this data. In this exercise, you're not supposed to see how the data is being generated. Okay, but I will sort of reveal the secret to you. I used a random number generator in NumPy, set the channel to 1, 2, 3, so that when you run this, you will also see the same results. Even though they are randomized, you will see the same random results as my slide here shows. All right, and we set the number of random numbers to be 200. So give me a list of random numbers following normal distribution. All right, centered with a mean of 2, standard deviation of, sorry, mean of 5, standard deviation of 2. Let's call that a set of 200 numbers, V. Then we generate again 200 random numbers with a chi-square distribution, call it W, Poisson distribution, call it X, and normal distribution, again, call it Y, but different mean 0 and standard deviation 2. Okay, what I've done is I know that all these numbers, these 200 numbers in column V and column Y, they follow random distribution. Therefore, when I plot them, all right, using scatter plot or else anything, if I plot them with a line plot or a dot plot, I should see, roughly a bell shape. Okay, I know that because I generated the data, and now you also know that. I'm trying to say that if I save this DF2, all right, and additionally, I derived Y and W. So Y is a linear combination of X and Y. Let me see. So I overwrite Y here. All right, so Y is basically a linear combination of X and the original Y, and then I overwrite Y. So in other words, Y is connected to X. All right, Y is connected to X in this fashion because mathematically it's derived, right, from X. And likewise, V, I have a mathematical relationship, but this time it's non-linear. So W is connected to V and the original set of data in W by this fashion. So V squared, right? The values in V, they are squared, and then they are added to original values in W, and what? And added with a constant 200, and then replace the original set of data in W.